Hello friends, in this lecture we will be discussing bases. As I said, I am going to complete this series by defining bases and giving you some idea and some examples. Okay, so let's start. So the word basis, I want to define a basis. So basis offers a vector space. So I let my V is a vector space over R and S is a subset of V. S is any subset of V. I am not considering subset, it is any subset. Okay, so it could be empty also, we'll see after some time. So it is any subset of V. This S is satisfying two properties. The one property is my S is generating V. Now we know the idea of generator and the linear combination are interrelated. If I say my S generate V, that means if I take all linear combination of S, elements of S, then I get V. It means I can write my V is same as L of S, or you can say my V is same as span of S. Both has the same meaning, right? Generator means it is the smallest subspace which is containing S. That idea is there. So both are okay. Second, my S is linearly independent. If my given subset satisfies this two property, then we call S is a basis of V. Why is that so? Why we call it as a basis? Because if you see, my elements of V are really special. The first thing, it is going to generate my entire V. And the second condition over here is also special. Why don't we say a set generating is a basis? Because we know that there could be many generators, right? My generator could be different, your generator could be different. Similar way, basis can be more than one. That means I can find out a different basis for a vector space and you may find out different basis. I am concluding that bases are not unique. That could be different. But then why is it so we are interested in these two properties? Okay, let's see some example and some more ideas about it which will help us to prove and gain some knowledge about basis. Okay, we will see some simple examples. Suppose I consider a vector space R2. R2 is a vector space over R, right? And I give you the set S, which is nothing but 1, 0 and 0, 1. The first thing I want to see, is it a basis? That means what? I need to check two things. Is it generating? Is it linearly independent? If it's so, I am done. I will conclude this S is nothing but the basis for it. Okay. So let's conclude. So clearly I can see if I make linear combination of S, I can find out entire R2. Right? How will you guys prove this? This is subset of R2, that is trivial. You consider any x comma y from R2, then what you will see, this x comma y can be written as x times 1, 0 plus y times 0, 1. That means it is linear combination of these two elements, and hence you can conclude this. The first one was easy. Now we will prove that this is linearly independent. How can I prove the given set is linearly independent? I will make a linear combination and try to see what are the ways to reach 0, 0. If there is the only trivial way, I will conclude it is linearly independent. So what I consider, alpha times 1, 0 plus beta times 0, 1 is equal to 0, 0. That means alpha 0 plus 0 beta is equal to 0, 0. Alpha beta is equal to 0, 0. Implies alpha is equal to 0, beta is equal to 0. That means what? I try to make a combination, I found there is the only trivial way, 0, 0, right? Considering them to be 0. That means we found that there is only trivial way, hence I can conclude my S is linearly independent. My S is linearly independent. Hence I can say S is basis of R2. Okay. Now as we see, now we will see the importance of these two conditions. The first one is necessary, because if it is generating, then only we are interested in it. But the second word, the idea of linearly independent, is really important. Is it okay if we avoid that idea? Let's see why we can't. Suppose in the same example, I change my S by something. I change my S by this. This set S is still generating my R2. Correct? So adding that extra condition of linearly independent does one thing. Now suppose in this case, if I try to check, is it generating R2, I'll get yes, it is generating. But if I try to go to check the linearly independent condition, I will see this set is linearly dependent. Since I can write this as a linear combination of these two. Hence, the idea of linearly independent, make sure that you are considering the smallest possible set. Okay. So, this way both the conditions are necessary and the ideas are such a way you get the smallest possible set which can generate the entire vector space. Okay. You can find out different examples for basis for R2. Okay. One note that I want to give, we know that inside this 0, 0 is a subspace, right? Is a subspace of R2. It is a subspace means what? It is itself a vector space, and I give you a theorem without proof that every vector space has a basis. If it is a vector space, it must have a basis. So this means what? This is a vector space, right? This is a vector space. It must have a basis. What could be basis for this? This is an interesting question. What could be the basis for this? Right? So the basis for such a set or such a vector space, that means a zero vector space, is defined to be phi. Yes, this is right. Basis for singleton 0 is defined to be phi. Okay, this is a note for you guys. And also one more interesting thing, the number of element inside the basis is called dimension of it, and every vector space has a fixed dimension. That means what? I told you that can be different bases, means I can find out some different bases, you can find out some different bases for the same vector space under the same operation. But what will be the same between my answer and your answer is number of element in that basis. If I get 2 element, then you will also get 2 element if we both have calculated in a connect pattern. That means if you are trying to find out different bases for R2, you will observe that all the bases will contain 2 elements. Okay, they might be different some way, but they will contain 2 elements only. Similar goes for the all vector spaces. They have the same number of element in any basis that you find. Inside R3, I can give you different examples in which you will find there are 3 elements, but all of them are bases. There are different bases but having the same element. Number of element in the basis is called dimension of that vector space. Okay, so this is a vector space. It has no element inside its basis, and this is considered to be vector space of dimension 0. R is nothing but vector space of dimension 1. What is the basis of it? 1, singleton 1. Right? This is a basis for R, real numbers. Okay? So these are some ideas that I wanted to tell about bases. Is there anything left out? I don't think so. If is it so, you write in the comment box the doubts you have. We will discuss it. Okay? Thank you so much for supporting me during this series and watching this video. Thank you.